rather than writing your own device support, finding it from somewhere else, because a lot of things have already been written, and so we may be able to find and use somebody else's code rather than writing our own. And if we've got all this code, how do we actually manage the I/O modules that we're making use of? So I'm going to be talking about what I actually mean by I/O support here, a quick review of the IOC development environment, and how that actually works to make this stuff modular. We'll talk about the development areas as components, and distinguish between support modules, which are things that contain device support usually, or drivers and that sort of thing, and IOC applications, and how we manage change in those in support modules versus in IOC top areas. Various different ways to support the I/O devices, and how to go about finding existing drivers and device support that's already available, and what you do to actually deploy it, installing it, and actually making use of it within an IOC. So by I/O support, I really mean stuff that actually connects record types to real hardware. At minimum, that's going to contain device support, but device support may include, may call some other code, which we would may call driver support, or it may be some external library. I/O support may include record types. It may be specific record types for particular kinds of I/O, such say ASIN has its own. There's an ASIN record for doing debugging and development purposes, so that counts as I/O support. And also any other software that you actually need within those layers. It's not necessarily EPIC specific code. It may be manufacturers' libraries or so on. Our support that we need may comprise multiple separate software packages. So to actually talk to a particular target device, you may need to use, say, DrivIPAC, because this interface is over a serial device, and you're using an IP module, the Octal 232 serial IP module. You may need ASIN, because that's how your device support communicates, and you may need then the device support, which might use ASIN, or you may be using the generic ASIN device support, and so on. So there may be multiple modules associated with I/O support to connect your record type to the hardware. And I/O support may also provide database templates, state notation language programs, MEDM screens, and so on. Synapse is an example, obviously provides all those for Beamline devices. But that may not be appropriate for all kinds of I/O. So there are some things that won't necessarily come with MEDM screens or whatever. That's very much specific to the particular device. Let's quickly review then what our IOC development environment looks like. For those of you who were in the IOC development course, we have things in a top area. We call this thing a top. Basically, it's a collection of directories and files that we develop the code in. There's a configure directory inside top, which contains a couple of important files, the release file and config or config site, more nowadays. And there are other files in that directory that are associated with the build system. There may be a series of app directories that contain source directories or DB directories that provide the C and state notation language sources, DBD files, database files, templates, and so on. We may have an IOC boot directory, which itself contains an IOC subdirectory for each of the IOCs, and those in turn contain startup files and so on. And then those are those three top areas: the configure, the app directories, and the IOC boot are our sort of source code as far as this development top is concerned. And when you build those things, the results get installed, copied into the installation directories. So DBD and DB directories for database definition files and database templates or database files. If they're header files, they'll be put into an include directory, and then any binaries that get built will go into an architecture-specific directory under under bin or for libraries under lib. So we basically separate out the source stuff, configure the app and the boots, and the installation directories. That whole structure and the rules that we use for our makefiles are designed to encourage modularity. So we can build up an IOC out of many components, and internally within Epic's base, these things are built separately. So channel access is built separately from the database access stuff, from the scanning code, other core libraries. The record and device driver support have their own library, and so on. The database is separate. So we have many components that we're combining. We explicitly do not have to have all those components defined in the same top as the IOC itself. I mean, as I said, most of that software comes from base itself or from Synapse, so we actually need to be able to link to and pull in code and definition files from these other top areas. As well as also providing additional components, these top areas can even override and replace some of the components from base if need be. So a few years back, there was an essential patch that needed to go into base, but we weren't actually able to rebuild base. We didn't want to have to rebuild base I'm talking about the accelerator systems here. We didn't want to have to rebuild base and all 250 IOCs out there. So what we did was we added a new support area called base patch. And in that, we overrode the components in base itself that fixed the bug that we needed to fix. And then we just changed all our IOCs and made them include or link to that additional base patch area before they actually linked into base. So what happened was our replacement was used in place of the original buggy code that was actually came with base. So and this is part of the deliberate design to allow us to do that kind of thing. The individual configure release file for the application that you're actually building determines what other areas are going to be searched for the components that we're making use of, and also, importantly, in which order that search happens. And so usually those searches, it will search those areas, and once the first one it finds is the one it takes. So if there's another definition, say, of the scan menu scan.dbd, that appears before the version in base, you can actually add new scan periods and create new periodic scan tasks by putting a new definition for the menu scan.dbd in advance of the one, i.e. higher up in your release file than Epic's base. So that's why there's a comment in the configure release file that says Epic's base usually appears last, so that other areas can override and replace components in base because of the way that search order happens. So we want to search base last so we can override it. Note that those searches actually only check the installation directories for those other top areas. So the include, dbd, db, and the bin and the lib directories. We never search the app directories or the IOC boot areas or those other things. So those directories are we're only searching the installed components. We're not searching the source code itself. So you can have a private copy of a menu scan file without replacing it for all the users that may actually need to use that. As long as you don't install that menu into the top-level DBD file, it won't override what other people are using if they're using your libraries. There's this distinction then between support modules and IOC applications. And certainly as far as the accelerator goes here, we distinguish between the way that we manage those. The top areas that provide components are our support modules versus the top areas that actually build the IOCs that actually run the machine. Certainly things like record support, device support, driver support, and Epic's base itself are usually shared across many IOCs. And we really wouldn't want to have multiple copies of those source files, and that would be a recipe for disaster, and you'd never fix bugs properly. we have different engineers who are maintaining the device support than the guys who are actually maintaining the IOCs themselves. So I maintain certain device support, but I'm not responsible for any of the operational IOCs. Importantly, the life cycle of the two different kinds of top areas are usually very different. I can release a new version of DrivIPAC, but the IOC guys, I don't want my new version of that code to be installed in all the IOCs that are out around the ring, unless the guy in charge of the particular IOC knows about it, because I may break something. So the life cycle, my installations, I may actually have multiple releases of these as somebody reports a bug, so I put out a new version. I don't necessarily want that version to go to all the systems without them being properly tested. So the life cycles are usually handled very differently. Areas that provide our components, the libraries then, are support modules, and areas that build IOCs, we call IOC application areas. And so the way that we manage them, the paths here don't actually match reality, but you might do them in all your support modules appear under the particular base area /module/ and a series of directories, whereas the IOCs appear under that base version number /IOC/ and so on. And then the IOCs themselves use their configure release file to point to the particular support modules that they actually need to include the components from. IOC areas can and often do contain local record device and driver support, but usually those are going to be for unique hardware only. So if this is a one-off that was built in the lab and there's only ever going to be one of them, there's no problem there in putting that support code into the IOC application that runs that particular piece of hardware. But if you're buying something generic off the shelf, it would really be, you may only have one now, but you may buy 20 more in the future, and so you don't want to put that code into the IOC area. You want to make that a shared support module. We usually only change support modules when we're actually fixing a bug, or if we're adding new functionality. And my philosophy is that the engineer responsible for the IOC is the guy who basically says, yes, I'm ready to take that new version, or I need that bug fix, so I need that new version. Because bug fixes can introduce new bugs elsewhere, and new functionality may break existing applications. So the guy who's in charge of the IOC is the one who needs to determine when he actually uses that. So support modules, then we install them, and once they've been installed, as far as the accelerator goes, we never change them. They're built for all the architectures we need, and then they're effectively made read-only. We do not change them afterwards. If you have a new version with a bug fix, we install it alongside the old one. So the version numbers are important for the support module. And then the IOC, the guy in charge of the IOC subsystem, can then say, oh, I need that bug fix. He changes his configure release file to point to the new version, rebuild the IOC, and now he gets that new code. But that's as part of his managing the IOC code. He's the one who actually makes sure that the change happens, not me, who's responsible for getting the support module built. This is something that we don't do terribly well, at least the accelerator side of things doesn't really document what changed in all the updates necessarily of the support modules, certainly for support modules that are managed internally. That's why I sort of try and keep release notes up to date as to say what's new. But we may have multiple copies of the same support module with a different local version number on it, and there's probably no documentation to say what's different. Usually it's just that you've had to link to a new version of some dependent module that you depend on, but there may also be bug fixes that occur, and we don't document terribly well what those are at the moment. IOC applications, in contrast to support modules, IOCs, certainly as far as the accelerator is concerned, and I'm sure for beamlines as well, you're going to change those very frequently in small ways. You update alarm limits, you change your sequence program subtly. You're adding new I/O points. You're adding an extra motor here, or a filter wheel, or anything like that. It needs to be relatively easy for that IOC application to be modified. You really don't want to have elaborate version control procedures that mean you have to get forms signed in triplicate, sent in, sent back, and so on, to actually make changes to the IOCs, because you need to get the machine working. You need to be able to edit those files and rebuild them immediately. But we also it's important to retain the history of what actually you did. And certainly as far as the accelerator is concerned, we do keep all our IOC applications in version control, and so we can very quickly go back and say, oh yes, we made that change, that's why you fixed this, but that broke that. So we have to work out how to, what the difference was between this week and last week. That's how we can check that out. So we can back out of any changes and recover if there are any problems. So this requirement of managing IOC applications then is very different from how you manage the support applications, where you build them once and you never change them again. You wouldn't want to have to create new releases of your IOC applications all the time. So the two we use different approaches to manage the two different things. And that then reflects on procedures and so on that get used for formal stuff as far as running the accelerator is concerned. Different ways of supporting I/O devices. If you've got device support, driver support, record support that's specific to the particular piece of hardware, then that's obviously best to use that if you can do so, and especially if there are going to be multiple copies of this particular device. You can hide the communications protocol from users and make things easier to do. And for complex devices, in many ways, you have no choice. You have to write particular device support. But for some things, you may be able to use generic support. So there are generic device supports for talking to VME register devices and so on. So you can use that generic stuff for talking to specific bus serial devices, network devices. And in that particular case, then, the device-specific knowledge often actually appears in your database records. So it's harder to understand what's going on from a user perspective, because they're getting all this detail about how you actually communicate to the device, that you need to write to this register before you write to that register, and so on. That's all encoded in the database design itself, which is so actually it's harder to understand what's going on there. But if you've got a one-off piece of kit, maybe that makes more sense. But for very complex devices and protocols, you may not be able to use that generic support at all. Sort of a midway, which we do actually recommend, will be something like the Stream device. We'll be talking about Stream device later on in the lecture series. That's a way of writing hardware-specific device support for message-based serial-type devices, but using a generic software. All you have to do is you're writing a protocol file which defines the particular messages that you're sending. And that protocol file then is the thing that takes this from completely generic to making it specific to that particular device. There's some information, a little bit more information that appears in the database, but that seems to be perfectly acceptable, and that's certainly a very well recommended way of interfacing to serial type devices, GPIB and so on. How do we find out if there is already a driver for this piece of hardware that someone has presented you and said, support this? Obviously, ask on the local site, talk to BCDA if you're one of the CAT users here, see if they already know about it. If you're using Debian Linux, then LightSource2, NSLS2 has a repository of EPIC stuff and so on. Here, obviously, we use Synapse, so Synapse is the first place to go to check that. If it's not available there, then we have this supported hardware database through the EPIC's website, where you can actually look and see what drivers people have talked about. You may or may not find links to the actual software there, but if there's no link to the software, there's usually a contact name that you can email instead. You can also look at collaboration meeting talks from the EPICS collaboration minutes or from past meetings, see if people have talked about devices there. And also check for postings on Tech Talk. If you can't find the device mentioned, then obviously post a message to the mailing list and see if somebody else has done it. It's much simpler, obviously, to install somebody else's code than it is to have to write your own from scratch for more complex devices, at least. And even Google searches, I found things that I wasn't aware of just by typing EPICS device support and a module name. Didn't appear in the hardware database, and then I wasn't aware of, because people do actually publish these things. They just don't necessarily tell us about it. You may find as part of that search that you get you get some code that was written for an earlier version of base. 3.13 drivers are, in terms of the actual code themselves, relatively similar. There's not much in the way of change needed to actually port them to 3.14. It's a little bit more complicated to actually, if they were written for 3.13, they had to be VxWorks specific. If you need to run it on RTEMS, that's not obviously going to apply to the people in this room, but at the moment at least. If you need to run things on RTEMS, then you need to port to use devlib instead of the VxWorks driver libraries. But that's actually relatively straightforward. It may already use devlib, in which case then great, that was available in 3.13. But there is actually a document on the EPICS wiki that talks about converting code that was talking to the VME, to the VxWorks APIs, to convert to devlib and hence make it completely operating system independent. So if you find you're in that particular case, I recommend looking at that library. It talks about some of the more obscure APIs that we used to provide that were sometimes used in device support, which you probably want to avoid using nowadays. So that document is definitely a good first step for porting. I really don't recommend trying to write Linux kernel drivers. If it's a straight register-based device without interrupts, then you can use those PCI to VME adapters. If you have interrupts involved, it gets more complicated, and you really don't want to have to write a Linux kernel driver. So I would recommend avoiding that if you can. Serial and network-based devices, though, device support can be made as portable as base, and ASIN makes that even simpler still. So that's definitely worth using if you can. Finally, once you've got hold of this module, how do you actually want to deploy it? Well, deploy is there's two steps. So we have to install it, and usually they'll come with installation instructions. If there's a Synapse README file, then you may have a slightly different configuration system to include it into the Synapse build. Almost certainly, though, you will need to have base built and any other support modules that you're relying on. So installing it usually implies building it. And to build it, we need to untar it. Usually, it's just a matter of setting the configure release file to point to the things that you depend on. So EPICS base has to point to wherever you can find base. If you have other modules that it depends on, we have to set those. And don't forget that you can use variables, makefile variables to simplify those paths. Those support module variables do actually need to point to absolute paths, though. We can't use relative paths in the release file. And once you've modified that, usually it's just going to be a matter of building the module to run. So you run make. There's a couple of little things that we use if you want to record the output from your build while you're seeing it at the same time. Then T is your friend. And then the build checks the release file, makes sure that it's consistent with all the support modules you're linking to, and then generates the files, runs through and compiles everything and so on. And hopefully that will be sufficient to succeed. So that's built the module, and now you would then need to link it into the IOC, and that's the steps for that are usually specific to the support module, but in general, again, you add the new module to your release file, and then you'll need to edit your make file to tell it what library to link in to find this code. Add the DBD files, or you may actually, there's two possible methods for that, and then there'll be startup script lines you need, load any databases, instantiate, and build the IOC and so on. So that's basically the standard steps, and